Today we're going to talk about the integration of collective behaviour with social evolution, about why it's necessary, and then an example of how we might do this. So from the micro to the macro, from cells to cities, collective behaviour is all around us. That's collective behaviour. It could be defined quite often as how individual level interactions produce emergent group level properties and why these evolved. Now I'm focused on this latter question of why they evolved, and when we want to understand the evolution of something, we often look to the benefits, and collective behaviours across nature can be seen to provide many benefits. Termites that build hills, mounds that have all sorts of intricate adaptive features like thermoregulation, animals that can navigate more efficiently as a group, for example salmon, birds in flying V formations and can save energy by doing so. There are examples in ants where they can form rafts to protect themselves against extreme weather conditions. There are foraging networks in vultures, gradient sensing in many species, including fish, and often collective behaviours can also provide anti-predator benefits. However, and this is a big but, you cannot take a group benefit and infer trait evolution. To recount a well-known historical mistake of this type, Wynne Edwards in 1962 proposed that animals behave for the good of the group or the species. Some caricature examples involve animals getting together and deciding that their population size is too many, so perhaps no babies this year. Well, it doesn't take much to go beyond this and think it would only take one or two to not obey by this strategy and go and cheat and have their own babies and pass their own genes on, and then thus their genes, their selfish genes, would grow in the population. So this almost caricature example of a mistake has led many to completely reject group level benefits, that we should totally ignore group level phenomena as a explanatory factor in the evolution of a trait. However, many theorists have pointed out we don't need to ignore group level benefits, we just need to consider them alongside the individual level fitness effects. This theory, known as multi-level selection, is actually mathematically equivalent to another well-known theory in social evolution. But whereas multi-level selection is partitioned into the fitness effects of between individual competitive interactions and between group competitive interactions, inclusive fitness is partitioned instead into the cost benefit of a social behaviour to their genetic relatives and the cost benefit of a social behaviour to themselves. So two questions I'd like to address before continuing are firstly that which theory is better suited to the evolution of collective behaviour, and do we really need two mathematically fit equivalent theories? Perhaps we could make do with just one. So firstly, which theory is better suited to the evolution of collective behaviour? Is it inclusive fitness? Many collective behaviours in genetically related species, highly genetically related species, are often a lot more complex than those collective behaviours in low genetic relatedness species. For example, in the social insects, but also in slime molds and other clonal species. But I would point out that high relatedness is not a defining characteristic of collective behaviour. What is that it's these individual level interactions that produce group level properties. And multi-level selection naturally fits this hierarchically structured field of study much better. Does that mean we do away with inclusive fitness in our understanding of collective behaviour? Not at all. In fact, Jonathan Birch has pointed out that the two theories can be combined in some cases and could lead to some fruitful insights. So perhaps for things like social insects, we could combine inclusive fitness and multi-level selection. So do we really need two mathematically equivalent theories? Let's say, to run through this, I'm going to give an example of a population in which it has a total random mixing, so there's no genetic relatedness, but there are between individual and between group effects in the population. We could say that between individual, it hurts to cooperate. You're better off cheating. But between groups, it's those groups with more cooperators that have a higher fitness. Now, the inclusive fitness approach would be to combine in some way, some relevant way, these two forces, and actually just say fitness is a composite of these two forces. And what we really want to know is whether the defect gene is going to grow in the population or the cooperation gene is going to grow. What really doesn't matter is distinguishing it into between individual and between group components. That's the inclusive fitness approach. But let's say we have a population where it really does matter. So let's say we have an intergroup conflict between many groups in the population. The more yellow individuals they have, the more cooperative individuals they have, the more likely they are to win a fight. So the team at the bottom is more likely to win than the team at the top. But if only a few casualties happen, then the selfish strategy, because they're hiding at the back of the group, they might be less likely to be the ones who actually suffer the impact of this intergroup conflict. Now, the reason I run through this toy population with you is because in order for me to explain this population and the dynamics involved in its evolution, I needed to refer to the between individual effects, so red beats yellow within a group, and I also needed to explain the between group interaction, so more yellows means more likely to win. The plot at the bottom, which has combined these two understandings, has does not tell us about the causal factors which influence the evolution of a trait, whereas the two plots above tell us about the causal pathways. So it's not just what evolves, but why things evolve. Science is about explaining why things evolve. So if the population really requires you to distinguish between the between individual and the between group components in order to explain the system, then multi-level selection might be a better fit. So here's where I pivot into a case study where I show now an example of how we could actually use multi-level selection to study the evolution of a collective behavior. And I'm going to give a specific example of the evolution of coordinated, that's coordinated, and I'm defining coordinated as this like aligned flocking behavior that you see in birds and fish in response to predation. And so we have a system where there are two levels of understanding. There's the individual level selection story. This starts with what I consider a seminal paper by Wood and Ackland using the Cousin et al. 2002 flocking model, where they showed that there are two evolutionarily stable flocking states. If the population can all form an aggregation strategy where each individual is trying to maximize their position with respect to the centroid of their local group. And then there's this other evolutionarily stable strategy where all the individuals in the group are aligned with each other. And once the population hit either the aggregation equilibrium or the coordination equilibrium, the population sticks in this state. It won't evolve between the two. Okay, so in 2021, you would have found me chasing flocks of pigeons with robotic falcons, with GPS trackers on the pigeons and the falcon. What I found was that the pigeons did not try to maximize their position with respect to the centroid of the group. They did not aim for the middle of the group to perhaps be safer from the falcon, even when there was ample room to move into. They could have easily, based on their turning angles, moved into the center, but they chose instead to align with the orientation of the group. So it got me thinking more deeply about this model and what it really meant. And what I got thinking was that in the aggregation equilibrium, if you added a liner to the group, that it must be the least fit individual. So what I'm saying is that when the predator came along, it obviously preferentially went for aligners in groups of aggregators. And this is actually a well-known effect. It's called the selfish herd effect, and it's essentially, the reason being is that the red individuals more closely huddled to the middle are safer when predators attack on the periphery of the group. Here the aligner or the coordinator ends up on the periphery more often than those trying to attract to the center, and that's why they are more predated. But what it's also telling me is that in a group of aligned or coordinated individuals, that the one trying to aggregate to the middle of the group is also less fit, because coordination is a stable strategy as well. So not really knowing why this is the case, because I thought that the aggregator would be more safe than the coordinators. I devised a series of in silico experiments where I play around with heterogeneous groups, and what I found was that although the aggregators try to aim for the center of the group, as they're trying to get to the middle, they're consistently having to make little left and right movements, whereas the other individuals in the group are always heading in the average direction of their local flock mates. What this meant is that the aggregators, despite trying to aim for the middle of the group, more often than not ended up at the back. Now, in highly mobile groups, this is where the predator more likely attacks from, just because of the way that the trajectories work. In a highly ballistic or mobile group, the predator ends up having to curve around the outside of them and end up attacking from behind. And if the aggregators fall to the back and the predator attacks from behind, you guessed it, the aggregators are more likely to be attacked. And Mike Kant came up with a nice title for the paper for me, which was Selfish Herders Finish Last in Mobile Groups, referring to their rearmost positions and their lower fitness in mobile groups. So let's plot this a bit more generally now. We might say that there's a certain risk of predation, and that this depends on the number of coordinators in a group, where a yellow individual to keep consistency is a coordinator and a red is the aggregator. And in all the worked examples, we're going to say that the group size is 5. So you've got from 0 to 5 coordinators, and in a group with 0 coordinators, it would have 5 aggregators, and so on and so forth. There's a baseline risk, which is 1 over n. So that's if both strategies had the same fitness. Every individual would have a 1/5 chance of being attacked. And then to work with the data that we saw, we'll say that there's an additional risk plus D to the rare phenotype. So that was if you were the one coordinator in a group of aggregators, you have this additional risk of D, and likewise, if you were the rare aggregator in the population of coordinators, you have this additional risk. Now, when neither strategy is rare, So in this case, it's impossible to have a group of 2.5, but it's possible if n was a different number. We say that they meet each other in the middle. This is an assumption. We would need to relax this assumption if we wanted to understand the importance of them meeting in the middle here. This is an assumption to keep it general for now. And then we might plot linearly through this point, but this doesn't quite work. We need a total risk of 1 for every group composition, and this just doesn't work. 1 over n minus d times 4, because the coordinators, let's say the point at the bottom of this linear slope is 1 over n minus d. 4 individuals in the group are going to have this risk, and 1 is going to have 1 over n plus d. Now this doesn't equal 1, it's less than 1. So what we need to do is assume that this linear relationship is the additional risk or safety to all of that phenotype in the group. So it's shared amongst, so this yellow line is the additional risk or safety, but it's shared among the number of all the coordinators in the group. So you divide the difference between the baseline risk, 1 over n, by the number of coordinators, and you end up with a curved line like this. You do the same for the aggregators, and you get plots like this, where the total risk is equal to 1. 2 remaining points needed to be added to this plot, and that is when there are 5 coordinators in the group. Obviously, everybody has the same strategy, so the risk returns to 1 over n. And also when there's 0 coordinators in the group, only the red line goes to there, and every aggregator has a 1 over n chance of being predated. And so this is really quite simple. And so what in the paper might look quite complicated, like what you see here, is really simply just what I've explained a moment ago. And part of me doing this video is to try to demystify some of the maths from the paper. Now, why aren't I simulating these results? Well, I'm looking here for a general model that can be applied more widely than just this example, really. So, yes, it involves predation, so it involves risk, but it could also be seen the other way around, where risk is perhaps value, so a value of a strategy depending on the group. And other reasons to not simulate are that I want to start with the pure mathematics, and then hopefully we can go on to test this model using simulations, but also potentially empirical data if we could devise virtual prey populations with coordinators and aggregators, quite a bit like how Christos Ioannou modifies the phenotypes of prey individuals and then sees how a real predator responds to these prey on a screen. And whilst we're here with the maths, there's a very important plot to show you, right? That the proportion of coordinators in the population is going to be given the value, the symbol p. And a very important plot to show you is the change in p from one generation to the next. So if p, so there's 0.2 proportion, so 20% of the population are coordinator, we can follow this arrow up and we can say, oh look, coordinators are more at risk. They have a higher risk than the aggregator. So the change in the proportion of coordinators from one generation to the next is going to be negative. At 0.5, we can see that the two strategies have the same fitness, so we say there's no change in the proportion of coordinators, and following on for the 0.8 condition. And if we were to do that for all of them, we get a plot like you see here. And this reproduces the two stable states we saw from the simulation models. If p is less than 0.5, delta p is negative, and so for every new generation, p gets lower because delta p is negative, and it gets lower and lower again, and eventually it hits 0. And that's where we have this aggregation equilibrium. And the other stable state, if p is greater than 0.5, delta p is always positive, and p, the proportion of coordinators, rises and rises and rises until it hits 1, you guessed it, the stable coordinator equilibrium. Now, that's the individual level selection story, but there's another component to all this. And it starts with myself looking very confused at my desktop. Well, actually my laptop, but it's easier to draw desktops. And what I noticed was that some simulations were taking an awfully long time to run, whilst others were completing quite quickly. And once I dived in a little deeper, what I found is that highly aligned flocks were, especially if the predator speed wasn't very high relative to the prey speed, that they would just get chased and chased around, and the simulation would never end because nobody would ever get caught. Whereas in groups with more aggregated individuals, being very slow moving as they're all trying to get to the center, they were very easily caught by the predator. Looking back at Wood and Ackland paper, they also found the exact same thing. And the coordinated groups are better at predator avoidance. But the approach by both Wood and Ackland and myself was essentially to just keep running simulations until one individual is caught, not to deal with this group level variation. It's not an immediately easy thing to think how to deal with group level variation. So we might plot this again in a very general way by putting risk over the number of coordinators and saying that, you know, as the number of coordinators increased, they were faster, so they had a lower risk. If you cut the predator off after a certain period of time, which seems likely and in keeping with a lot of observations from nature where the predator is quite often unsuccessful at hunting groups, you might say that the risk is decreasing the larger number of coordinators you get. And indeed, when I run simulations, I get data that look like this. I get a slope, a curved slope, but for the purposes of this, again, highly general model that we can improve on in the future, just to start with the basics, we'll put a linear slope through this. And what's more, we'll give it only one parameter, which is k, and say that it's linear between k and 1 minus k. So the research question here was, did we always get it right? Was it necessary? Is it going to necessarily always have two stable states, a system such as this? Or is it possible that the benefits at the group level for the coordinators could potentially destabilize the aggregation state and make coordination the only stable state in some instances? So that is, this has gone very jerky now. See if it goes a bit smoother this time. So instead of having the two stable states, there is just one. Delta p is positive for every value of p, and so p will rise in every generation until it hits 1, and the only stable state would be the coordination threshold. So the model works like this. There's an infinite population of asexually and perfectly reproducing individuals which have a proportion p number of coordinators. In the example here, it's about 50-50, but this is just a small subset from an infinite population, which I'll show you here. They then get randomly drawn into groups of size n, and although they were randomly drawn, there's variation in the groups. It's not that if the population has 50% coordinators, that every group has 50 coordinators, even under completely random selection of individuals per group, there's a distribution. So we can see the number of coordinators I've just given numbers to here, but they produce a frequency distribution such as this when p is 0.5, or something more like this when p is 0.2. It's when there's 20% of coordinators. And so, yeah, this is a binomial distribution, and the maths lingo looks something like this, but again, just simply random draws from the population. Each group then gets attacked once by a predator. Some groups manage to escape. And the chance that a whole group manages to escape is, as we discussed, a function of the number of coordinators, decreasing risk. And if the predator is successful, then your individual level risk is governed by frequency dependent, governed by what's going on in the group. If you're and we've discussed the individual level story as well. So the viability of any individual is 1. So that reason it's 1 is that's 100% chance of survival at first, but then it's you minus the risk to the group. So and then you multiply the chance that your group gets attacked by the number, if the group does get attacked, that it's you who is attacked, and you get a viability, and then the plot looks more like this. So viability or survival on the y-axis, and the number of coordinates in your group on the x-axis. Now, looking at this, you might still say, but coordinators still aren't the fitter strategy until they are over 50% of the group. So if we're looking at when there's only 20% coordinators, surely aggregation is the best strategy. We can see here that the viability of a coordinator is lower than that is for an aggregator when number of coordinators is low. But this is just completely ignoring what we talked about earlier, which is the frequency distribution of the number of coordinators. Because we have a variety of groups in the population, we don't just intersect one line of this plot on the left. We instead have to consider groups of all composition. So the number of offspring left by every group is the viability. So another model assumption I should say is that if you survive, you reproduce. So the number of offspring left over is the viability of each individual times by the number of coordinators or number of aggregators in their group, and times the frequency. So frequency of that group. So groups with 5 coordinators might have incredible viability, and so it looks like they're going to leave almost 5 offspring per group. But then if this type of group is extremely rare in the population, then it won't have a very large effect. So this goes through the same thing again, but now just draws an actual plot of the number of offspring over the number of coordinators. And just for these sort of toy parameters that I put into a software, and then I'm trying to replicate here with drawings, we take the fitness, which is the total number of offspring left by an aggregator strategy, denoted by WA, and the fitness of the coordinators by WC. And then the proportion of coordinators in the next generation is going to be P dash. And just using a total arbitrary set of parameters, I can easily get a P dash of 0.21, and because we saw that P was 0.2 in the previous generation, we can see how it's possible that delta P is greater than 0, so change in proportion of coordinators greater than 0 even when P is less than 0.5. But that was just an arbitrary example. We really want to run through the maths a bit. So we saw the individual risk, turning this equation into group risk, and requires multiplying or getting the viability. It requires multiplying by the group risk and then subtracting from 1. Special case when the number of coordinators equals n is 1 minus k, as defined earlier for the group risk, and likewise k is the risk when the number of coordinators equals 0, so the viability for the aggregator is 1 minus k times 1 over n, and so on and so forth. Now we have the viability. We want to get to the number of offspring. And this is just involves multiplying by the number of individuals in that group. And finally, to get the fitness, we need to multiply by the frequency of that type of group in the population. So we need to sum this term above here for number of cooperators equals 1 through 2 and all the way up to n minus 1, and then we want to add the condition for and we want to see the frequency of that type of group in the population. This is this binomial language I gave you earlier, and then we want to add the condition for when number of coordinators equals n. Now here it's quite handy that this part in the square brackets here can be rewritten in form, the square brackets including the nc actually on the end, but not including the binomial terms, can be rewritten as in the form of a nc squared plus b nc plus c. That's a nc squared plus b nc plus c, where a equals this, b equals this, and c equals this. I didn't solve this by hand. This is possible with computational symbolic maths. I use symbolic Python myself. But the brilliance of having it in form a nc squared plus b nc plus c is that the sum of the binomial and I've written it out as where nc is x here, and actually in the paper it's written with x as well. But when you sum up the binomial distribution of this quadratic, you get a a known result. So here we get what you see below, which is the sum of the quadratic from every number from x. Well, the thing is, this is from x from 0 to n. We wanted x from 1 to n minus 1. So simply to get from 1 to n minus 1, you just have to do the summation from 0 to n, but then subtract the expression evaluated at 0 and subtract the expression evaluated at n. And then we finally just have to add in our final condition. That was when nc was equal to n, or x is equal to n. That's just because that's part of the fitness function for those individuals. So we've got the fitness of coordinators. And yes, fitness no longer contains the number of individuals per group. It's just a function of p and n and k and d. And so great. So now we return to where we left off, where P dash is the proportion of coordinates in the next generation. We know that P dash is the fitness of the coordinator strategy, which is a function of P. I don't want people to be confused by this like I was when I started social evolution. If you have an open brackets and P, it doesn't mean it's also not a function of N and K and D as well. It's just that we're highlighting that it has P in that equation. What we then say is that we know the change in P from one generation to the next is going to be P in the next generation minus P in the generation previous. And the coolest trick in the social evolution handbook is the replicator dynamic. It says that when delta P is 0, we know there's no evolutionary change anymore because there's the proportion of coordinators is not growing or diminishing from one generation to the next. And when that equals 0, we know that the proportion of coordinators in the next generation, P dash, must equal the proportion of coordinators in the generation before. And so now we use just a different notation. So we use a P bar. P equals P dash, which also equals P bar. Now we can say 0. 0, remember it was delta P. And that equals P dash, which is this term here. And this is a function of P bar. And then minus P, which is minus P bar. And so now we can use, again, a symbolic library to ask, can we solve for P bar? Can we get a value that P bar, value of P bar that has no evolutionary change? And unfortunately, computer says no. It says that there are different solutions for each n. Okay, so let's go through systematically. What about when n equals 3? It says, okay, now I have some solutions for you. It says that when P bar is 0 and P bar is 1, there is a solution. And also, when P bar is 3dk plus 3d minus 2k plus 1 over 9d. And this is more interesting. Now, what is this value here? It's actually this crossover point on our previous plot of delta P over P. P0 and P bar equals 0 and P bar equals 1 are always the case, and you can see them on the plot. But we also have a third condition where delta P equals 0. So these are all the conditions where delta P equals 0, right? So we already knew we were going to have 0 and 1. But we have this interesting third case, which is in the middle, which is this pivot point between which we have two, over which we get the stable aggregation equilibrium, under which we get the stable aggregation equilibrium, and over which we get the stable coordination equilibrium. So back to the original research question, can this pivot point be moved so far to the left that we have positive delta P for every value of P? So we're thinking, can this solution for P bar equal 0? And a slight bit of rearranging, really easy high school algebra reveals that yes, you can if minus 3d minus 1 over 3d minus 2 is less than or equal to k. And we know that k must be less than or equal to 1 because this is the group level benefit slope, and you can't have a risk greater than 1 of being predated. So now we can plot group benefit k over individual risk d for this condition where n equals 3, and we can see that there's a threshold under which you have 2 stable states and over which you have only 1 stable state, the coordination equilibrium. And this is only for groups of 3. So now, feeling a bit more confident, I type in n equals 4, and I get a new slope. K equals minus 4d minus 1 over 8d minus 2. Looks like a pattern emerging here. Let's type in 5. Oh yes, we have a very clear pattern where we have n minus nd minus 1 over n times n minus 2 in brackets d minus 2 is less than or equal to k. And the solution obviously has to be k is less than 1. And when that's the case, we can solve for d, and we say that d must be less than or equal to 1 over almost n squared. You've got n times n minus 1. It's really a very rapidly decreasing d for a larger n, and that d is the difference in the risk for the rare phenotype. So if n was 10,000, could this model be used to study starling flocks? Perhaps not, was my first thought, because if n is 10,000, then you need an individual risk of the new strategy to be lower than almost 10,000 squared, and it might be seemingly impossible. So the worst ever starling murmuration here, and perhaps we need to go a lot higher than some threshold if this sort of model were to explain their highly coordinated movements in flocks such as this. But if there are potential extensions to the model which can be done, which is to relax the assumption of n being a fixed number, so n as well as nc could have a distribution. Now in this model, the cooperative, the beneficial strategy, it evolved, and there was no need to add any assortativity into the model. Assortativity is that non-random likelihood of like phenotypes being in groups with phenotypes such as themselves. So to go through assortativity, what it might look like, what we had was a number of coordinators taking distribution forms like this, but if there was assortativity, you might have a bimodal distribution. Now, most multi-level selection models require assortativity for the cooperative phenotype to evolve. Why did mine not? It's essentially that most multi-level selection models are modeling altruism. In this model, I didn't model altruism. It's a cooperative behaviour, but it's not always detrimental. Altruism is, in the definition of altruism, it implies that the cooperative behaviour is always the negative thing to do within a group. Between group, it's potentially positive, but within a group, it's always a negative has a negative impact on individual fitness. But this isn't what I modelled. I had a frequency-dependent fitness within a group. That risk depended on the number of coordinators. So that explains why assortativity wasn't needed. But assortativity would probably facilitate the evolution of collective behaviour. And so I think that this could potentially be, and also assortativity can emerge naturally in collective populations. This is a good paper to have a look at if you want to see about that. It's in PLOS Computational Biology. And potentially, by including assortativity, we could help integrate kin selection into my framework of multi-level selection to study the two alongside each other when studying an evolution of a collective behaviour. And potentially my next model could be to do that. So if anyone's interested in teaming up on that, then give me an email and I'll be happy to chat. So potentially a next model could be on that topic. I'd also really like to have a think about whether we could do a special issue on collective evolution, integration of collective behaviour and social evolution, where I get a broader range of perspectives from these social insect people, from these slime mold people, just to expand our understanding of the usefulness of social evolution in understanding collective behaviour. And potentially Phil-Trans-B would be a good outlet for that. But again, this is a reach out to any collaborators who might also be interested in submitting or co-editing, submitting for a co-editing of that. And with that, I'd like to say thank you for tuning in. I hope you enjoyed it and I hope it demystified the maths for you a little bit. Take care. See you next time.